Okay, I'm going to go over again the PN junction in terms of the energy band diagrams and the formation of the depletion region within the material. You got to remember at all times that the energy band diagram is just a representation of what is going on in terms of energy. And within your energy band diagram, you have to remember what's always indicated here is basically the level of energy within it. All right, but before we get into the PN junction, I think it's important for us to consider both the P-type and the N-type material. So I've drawn them at the top there with the valence band and the conduction band indicated. All right, so remember, any electrons that are within the valence band are not available for conductivity, but they can have, remember this is energy from valence band to conduction band. Those electrons can have, more energy, but just not enough to put them into the conduction band. All right, now I think it's easier first to start with the N-type material. What I want to consider is to where the Fermi level is within the material, and just to try and get it clear what the Fermi level is, because it can be a complicated enough kind of a concept to get your head around. But basically the Fermi level is the maximum energy that an electron within the material is likely to have. Okay, now if you consider the N-type material, which has an abundance of electrons available for conduction due to the donor dopant in the material, basically all hole states within the valence band are likely to be occupied. Okay, so what does that mean? It means that any P-type sites that are available within the material, basically due to impurities or etc., they're likely to have been filled with electrons because of that availability. All right, now as electrons are like particles, they don't like to be close to each other, like charges repels, so that basically raises the energy of those electrons because they don't want to be close to each other, but they can't not be as such within the material. So what that has the effect of doing is raising the energy of the electrons with the material. And what that does is it basically pushes the Fermi level towards the conduction band in the material. So basically that is an indication that the electrons in the material have an increased energy. On the other hand, if you consider the P-type material, because you have an abundance of holes within the valence band due to the acceptor type dopant impurities in the material, that means that there's plenty of hole states available in the valence band for any electrons to reside in. Okay, so that essentially reduces the energy of any electrons within the material. So in this case, that means that the Fermi level then is closer to the valence band, which is just an indication that any electrons within the P-type material are likely to have lower energy. Now, what happens when you put things together that have one has a higher energy and one has a lower energy? You see it in electronics all the time. It's the same thing that happens when you connect any power supply. Something will move from a state of higher energy to lower energy until there's an equilibrium reached. Okay, now when we go to consider the PN junction, what we're going to consider first is what's called thermal equilibrium. So basically this is as the PN junction sits with no applied voltage. It's called a thermal equilibrium because the state it reaches is only stable once the temperature remains stable as such. Okay, but if you can remember what we're saying, that in the N-type material, the electrons have a higher energy than they will in the P-type material. That means that when you put them together, those electrons are going to want to flow to a lower energy condition. Okay, and that's what happens. So going down here to where, say, we have a PN junction. So what's going to happen in this situation is you're going to get a movement of electrons from the N-type material into the P-type material. Okay, so what happens when they do that basically is, remember, in your P-type material, you've got your acceptor dopant. It's going to take on electrons that are coming across from the N-type material. When it takes on electrons, they're going to become negatively charged. So what's happening is you're starting to get all these negative ions within the P-type material. But equally on the other side, as the electrons are leaving the dopant donor atoms, they're losing electrons, so they're becoming positively charged ions. Now, you got to be clear what it means when I say positively charged ions. These are not charge carriers. These are basically dopant atoms that have essentially either lost their charge carriers from this side or gained the charge carriers from the other side. And this is what's changed their state. They were originally neutral, but after gaining or losing electrons, they have reached a charged state. Now, as I said to you, the electrons want to move from a state of higher energy to a state of lower energy. But as this starts to occur, it will reach a point at which it stops. All right? And why does it stop? The reason it stops is across here, you remember, we've got all these negatively charged ions. That gives you a negative potential. And here you've got all these positively charged ions. And that gives you a positive potential. And that means that there is a potential difference across this. And this is what is called the built-in potential. This is VBI. Okay, so basically you got to imagine if you're an electron on this side and you want to cross, you're now facing all these negatively charged ions. Again, your like charges repel, so it's only going to happen to a point where this charge builds to a point where there isn't enough energy for it to occur anymore. So it reaches an equilibrium state, a state that we can only change by applying a potential, i.e. either forward biasing or reverse biasing the junction. All right, but as I've indicated to you, this is the built-in potential of the junction. But as well as that, there's also a physical parameter to this, and that physical parameter is what we call W. And this is basically your depletion region width. This is your depletion region width. And this is a physical parameter, and we will look at how you can calculate that. Now, the other thing to understand, and maybe it will become clearer when we move on to forward or reverse bias, is the depletion region width is not a fixed parameter. When you put it into a thermal equilibrium state, yes, it does have a thickness that it will reach to. If you forward bias it, it starts to become thinner and thinner. So these move closer and closer together. Until you go into complete, you go above your threshold or your built-in potential, and your depletion region essentially is gone altogether. If you reverse bias the junction, this widens and widens. Okay? Now, there's another thing that's going to affect your depletion region width, and that's going to be your doping concentration. Okay? Because if your material is very, very heavily doped, what's going to happen is you're going to get a very, very narrow depletion region. Why is that? All right, because if this is a very high doping concentration, so that means that you've got more impurity atoms per cubic centimeter of the material. In order to reach a charge state, you've got so many more charge carriers within a smaller area that it takes less of them to reach this condition where no more diffusion can occur. So physically that will occur over a shorter region. Alternatively, if you put in a lower doping concentration on both sides, your depletion region will be wider. But that is something we will return to when we look at the Zener diode. The other thing about it is if you have an unequal, as I draw you these pictures, I'm showing you equal depletion regions on both sides. And that's basically, you're kind of making the assumption that you've got an equal doping concentration, both in terms of your p-type acceptor atoms and your donor type n-type atoms. If you had a situation where your n-type region was more heavily doped than your p-type region, basically you would have more charge carriers here. So in order to create an equal charge above it, you would have a narrower depletion region on your n-type if you had a higher doping concentration, and a larger depletion region on the p-type. So it would be asymmetrical if there was a variation in the depletion rate. But anyway, that might be getting off point a little bit. Right, in terms of the energy band diagrams from that, okay? So as I said to you, we put these together. Your electrons will flow from their Fermi level, they're of higher energy within the n-type material, to a lower energy within the p-type material. In terms of our energy band diagram, what does that mean? Right, basically what that means is you have an equalization of the Fermi levels within the material. The charges will flow until the Fermi levels are the same on both sides, i.e. there is an equilibrium reached. You don't have a higher energy on one side. So it goes to a point where the Fermi level becomes fixed within the material. And this is within thermal equilibrium. The only way we can make a change in the Fermi level position is to apply a potential to the device. Okay, so the Fermi level must become the same on both sides. But the thing about it is that the gap between the Fermi level to the conduction band in both sides of the material does not change. Okay, so it will stay the same on both sides of the material. Okay, so the gap between the Fermi level and the conduction band on the p-type will remain the same. And the gap between the conduction band and the Fermi level on the n-type will remain the same. But across your depletion region, what you have is what's referred to as a band bending. Probably should have drawn that with a bit bigger slope, but whatever. Okay, so there's what we call a band bending, but basically there's a difference in potential from the conduction band to the valence band. And what does that mean? Sorry, from the conduction band within the n-type material to the conduction band within the p-type material. And exactly the same thing will occur with the valence band within the materials. You get this band bending. Now, that gives us this energy difference. This energy difference between the conduction band within the n-type material and the energy difference between the conduction band within the p-type material. And that is basically what we call the built-in potential, Q VBI. Okay, Q is just the charge on an electron. And this is just what's indicated by this, but on the energy band diagram. There is essentially a difference in energy. So if you want to be an electron in the conduction band, this is the amount of energy that you need in the conduction band within the n-type material. But if you want to move to the conduction band within the p-type material, you need to gain this extra energy, which is your built-in potential of the device. And the only way you can do that is to have an applied potential, okay, which I will cover when we reach it in forward bias. But basically, this is in thermal equilibrium. And again, this parameter is W, your depletion region width. Okay.